Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Okay, let's continue on with the theory on statistics. Okay, a couple of things I want to get done in this section. Margin of error is one. We've touched on exam questions with that. It's a formula where your margin of error is 1 over root n. Okay, where n is your sample size. So what you find is the bigger your sample size, you can see that from these numbers here, the smaller your margin of error. And if you think about that for a second, okay, the bigger your sample size means you're sampling more people. So if you sample more people, then you're more sure of your data. You're more sure of the answers you're getting to whatever data you're trying to find out with your sample, okay? Or if that's parts that you're testing off a production line, for example, then you're more sure of your mean and so on and your spread of your data. So what you'll find is the bigger your sample size n, the smaller is the margin of error that you need to add and subtract to your sample. Okay, so let me go on and explain that. When you're setting up a confidence interval then, and we did an exam question on this, you take your sample data, okay, which is p hat, so its official title is sample proportion, okay. So what that means is you have looked at a proportion of a sample basically, and you add and subtract your margin of error to it. Okay, so what you're asking is you're posing a question, how many people gets up in the morning at 8 o'clock, for example, okay? So depending on the sample that you ask, you're going to get different answers for that. And then you might get 40%, for example, and then you add or subtract a margin of error to that, and your answer then, instead of being 40, because that's solely dependent on the sample that you asked, you'll create a margin of error around that where it'll be something like from 37% to 43% gets up at 8 o'clock in the morning. Okay, so you create a plus or a minus around that sample data that you have, so that you now have a confidence interval, as opposed to just one piece of information, in my example 40%. Okay, you cannot stand over 40% because you haven't asked the entire population, you've only asked a representation or a sample out of it. So that's why you have to protect your answer with a sample, with a confidence interval, or with a margin of error. Okay, and your margin of error, it can be done in terms of standard deviations too. That formula 1 over root n is you're being 95% confident when you plus or minus 1 over root n for it, because what you'll find is 1 over root n equates to 2 standard deviations. Okay, now 1 over root n was the formula used for margin of errors in all of the older papers. So if you're practicing exam papers and you're going back through the years, you will find that, and you look at the solutions on examinations.ie or wherever you choose to look at them, you'll find that they were all done, the margin of error was all done with 1 over root n. Okay. As part of the Leaving Cert, they then introduced the sigma p formula, which also sets up a margin of error as well. Okay, it's also called the standard error of the mean as well. And you can see I've just pointed it to it here. It can often be called SE, standard error of the mean, rather than E. Okay, and in that formula you have P, which is your sample. It would be the 40% in the example I took, times 1 minus P over N again, your sample size. Okay, and it's felt that this formula is more accurate than 1 over root n. Okay, so margins of error confidence intervals are now predominantly done using this formula here. Okay, typical sample size in any stats is greater than 30. Okay, 30 tends to be what's considered the smallest sample size of your known, or the smallest sample size that you can use. Don't get hung up between P and P hat. Okay, P is what we call the proportion of the population. So if I'm talking about the entire population, I will talk about P. Okay, or I will describe statistics in terms of P as such in this formula. Okay, if you only have a sample of the population, we tend to call it P hat. Okay, and we use P hat, a sample of the population, if we don't know P. Okay, but for all intents and purposes, it is the same thing. You'll only be given one of them on your course. So the only reason I'm pointing it out is in case you're looking at solutions or other books or whatever, and some might use P hat, some might use P. Okay, it depends how strict they are about the language of maths. Okay, all margins of errors typically on your course are done to the 95% level of confidence. And you'll see that with your hypothesis tests, it's all 95% level of confidence. Okay, so that equates to 95% here under the normal distribution curve. And you've 2.5% out here on the left and 2.5% out here on the right, or as a decimal, 0.025. Okay, so your margin of error is P hat 1 minus P over N, okay? But to be 95% confident, we multiply it by 1.96. And what you'll find is 1.96 is the Z-score equivalent for 0.95. So if you look within the body of the normal distribution curves or the normal tables, you will find at a Z-score of 1.96, you will find what you'll actually find is 97.5, okay, because of how the tables are represented in the tables. Okay, so what I'm going to do is I'm going to just open up a log tables for a second, because I just want to show you what I'm talking about. Okay, I'm going to stop sharing my screen for a second because I need to share my desktop, okay? So that I can show you. So you should be seeing the normal distribution or the log tables now. I'm going down to the normal distributions. If you can't, shout. Okay, so you can see from the tables that a Z-score equates to all of the 95%, but also the 2.5% on the left. Okay, so if I go down to 1.9 and across to 6 here, can you see that it's 0.975? Okay, so that's the 95% in the middle, because we want to be 95% sure, and the 2.5% on the left. Okay, so when you use 1.96 times sigma p, you are doing your margin of error to the 95% level of confidence. Okay, so that's where the 1.96 comes from in the formula. Okay, these tables are slightly different, but I was looking for a sigma p. They're not the leave insert tables. Let me go back and see if I can find a leave insert one. Yeah, it looks more like it. Okay, let me scroll down. No, that's the same. Anyway, not to worry. We'll find it again when we're doing an exam question. Okay, so just like before, you can set up a confidence interval where you take your sample data, P or P hat, and you plus and minus to it 1.96 sigma p, where sigma p is the square root of p times 1 minus p over n. Okay, so That is the formula that is used on any of the current papers for setting up a confidence interval, okay? And I just want to draw your attention to this little note here. It is worth noting that when P or P hat, if P is unknown, is close to a half, a good approximation to the margin of error at the 95% confidence interval is 1 over root n, okay? So when P is a half, okay, sigma p is very close to 1 over root n, okay? So there's a time when the two formulas will give you almost the same answer, and then you'll find there's questions where they'll be a little bit apart, okay? So use sigma p in general, okay? So that's the margin of error. Okay, and it leads me nicely on to hypothesis testing. Okay, so a hypothesis test basically is when somebody makes a statement and you have to prove or disprove it using statistics. Okay, and for example, because we're in COVID times, we could say that one of the drugs is better than the rest. Okay, we could say something like such. Okay, now those medical companies cannot come out and make such a statement unless they have the data behind it to back it up. Okay, I'm trying to think of some of the companies that makes the drugs. I'm trying to think of the one in Cork, but it's gone out of my head. Anyway, it doesn't matter. They can't say that their injection is better than any other one unless they have statistical data behind it to back it up. So the statistical process of making such a statement is a hypothesis test. You hypothesize that something is true, you test your claim, you make a conclusion. Okay, and they are the steps you must do in a hypothesis test. Okay, so the first thing you do is you write down what's called the null hypothesis and the alternative hypothesis. Okay, now it takes a little bit of practice to figure out what goes into the null and what goes into the alternative. But if you remember it as such, the null hypothesis is what's called the status quo. Nothing has changed. Nothing is better than anything else. There's no difference between anything. Okay, so the null hypothesis it's called H0. Okay, so for examples, if you pose the question, is global temperature increasing? The null hypothesis in that case would be, no, it's not increasing. There's no difference now as opposed to 10 years ago, okay? And then the alternative hypothesis, which we call H1 in many cases, I see this book calls it HA. I've always used H1, I'm sure it doesn't matter. The alternative is that the global temperature is increasing, okay? So if you reject the H0 and you accept the H1, so in other words, if the H1 turns out to be true, then that's the big revelation. That's big news. Okay, something has changed. Number 3, is a survey on left-handed people biased if it indicates that 24% of people are left-handed? Well, you're going to assume that the survey is not biased, okay? So you assume the status quo, happy clappy, everything is good, everything is even, and so on and so forth, okay? The alternative, the H1, would be the survey is biased, okay? So your H0 is the status quo. So the first step, I'm over here on the right. Where's my pen gone? I'm over here on the right. Write down H0, the null hypothesis, and HA or H1, the alternative hypothesis. So you write them down in English, okay? The alternative is the complete opposite of H0. Okay, and you should write them in a way that all possible scenarios are covered. You're either H0 or H1. You can't be anything else. Okay, and I'll go through an example of that in a minute where I explain that. You then do your test data. You test your claim. Okay, so you find out your population proportion. You can create a margin of error if you wish, and you test your data. Okay, and again, I'll go through an example of that. Okay. And then once you set up your confidence interval, you're going to see if whatever you're testing is within that confidence interval. And if it is within it, you fail to reject H0. So in other words, H0 is correct. If it's outside the confidence interval, then you're rejecting the null hypothesis and we're concluding that the alternate hypothesis is correct. And the last step, you state your conclusion in words. Okay, now in many of the marks I have seen for hypothesis testing, I have seen in many cases you get a third of the marks for writing down the null hypothesis and the alternative hypothesis. You get a third marks for doing the conclusion in words and just a third for doing the test, which is the bulk of the question. Okay, and what many students do wrong is they just do the maths part in the middle and they ignore the wordy bits top and bottom. Okay, so you could lose up to 2/3 of the marks if you do that, so don't do that. Okay, now the mathsy bit in the middle, there's a couple of different ways of doing that. You can do it with a confidence interval like this example is suggesting here. You can do it through Z-scores, or you can do it doing a p-test. Okay, and whichever one of those methods you choose, it does not matter. It kind of depends on the question that they're going to ask you in your Leaving Cert. The question is going to lend itself to doing it one of those three ways, okay? And it'll do that by the data that it gives you in the question, okay? If you have enough data, you can choose whichever way you like. Okay, it does not matter. It's all about comparing it to that 95% curve that's under the normal distribution that I have written all over here. Okay, so it's, are you within that 95% confidence area here, or are you outside it? So whether you find that out using Z-scores, where you're comparing it to 1.96, which is, as you know, the Z-score here and here for 95%. So you're comparing it to 1.96 if you're doing Z-scores. If you're using this confidence interval here, you're setting up a confidence interval and seeing if your data falls within it. Or as you'll see in a few minutes, if you're doing a p-test, you're seeing, are you out here in the 2.5% region, which is what, 0.025. Okay, so you're looking at your p-value. So they are all related, they're all similar, and they're all trying to do the same thing. Okay, so this, on a page, are you within the 95% inside? That's your confidence interval. That's where you accept your H0, or you fail to reject H0, or the blue bit on the outside here on this normal distribution curve. If you're in the blue bit, then you're basically accepting H1, the alternative hypothesis. Okay, so that's your hypothesis test, and that's where you are going. Okay, so that's hypothesis test. That's bringing me on now in the book to what's called the central limit theorem. Okay. Okay, so some of the questions that you will come across in your Leaving Cert, they are considering sample means. Okay, so let me read. Suppose, let me make it any bigger. No, it won't. Suppose a large number of different random samples, each of same size n, I'm just reading up here, are selected independently from the population with mean mu and standard deviation sigma. Each of these samples will have its own mean, x bar, and standard deviation, s. The set of these different sample means, x bar 1, x bar 2, x bar 3, are called sample means. If these sample means are represented with a curve, they have a distribution with the following properties, called the central limit theorem. Okay, what you find, there's three properties in the central limit theorem that's really important. The first one, super important, okay? Remember way back when we were doing stats, I said that an awful lot of phenomena falls within a normal distribution or a bell curve, okay? Well, if something doesn't fall within a normal distribution curve, however, you set them up into groups and you get means of groups, okay? when you consider the means, the distribution of sample means is always normal. Okay? A little bit hard to get your head around first, okay? But if something isn't normal, so in other words, when you plot a histogram, it's not normal, okay? Then if you group it into like subgroups and you get the means of the subgroups and you plot them then on a histogram, then you'll find the means will always be normal. Okay? The second thing that's really important when you're looking at means, okay? So the mean of means, when you get the mean of means, it will always be equal to, or you can assume it's equal to, the population mean mu. So in other words, the mean of means, you're no longer considering sample means. It's effectively just as good as if you got the mean of the entire population. Okay, so the mean of the sample means equals the means of the population. And the third most important thing is the fact that when you're looking at sample means again, and now this time we consider the spread or the variation of standard means, it's much tighter. Okay, so therefore you can take your sigma and you can divide it by root n. And dividing it by root n makes it a much tighter, smaller sigma value. Okay, so bear with me for 1 second now, and I'll just log on because I want to show you this in the log tables, because all of these formulas are there, and I have one here on my iPad. I just need to log on and show it to you. Okay, so let me stop sharing that for 1 second. Okay, so these are the log tables that I was hoping to find on the web. Okay, so I'm going on to statistics and probability. So if you come down to some of the things I want to draw your attention to, okay, is as follows. There's my sigma p formula that I was talking about. Don't forget to put the 1.96 or plus or minus 1.96 there to make it 95% confidence interval, okay? Okay, but it's this page I want to get onto, okay? So you can see that up until now, we have been doing the standardizing formula, Z being equal to X minus mu over sigma, okay? When you're dealing with means of means, your sigma gets divided by root n. Can you see that? Okay, so the same standardizing formula, except it's done with means, okay? So that's important. There's a version of that that is with means. Okay, so it's the same formula per se. It's just, is your sigma of a sample or is it of mean of means? Okay, so you can only see the difference of that through doing exam questions, and you're looking out for that word means written all over the question, and then you know you're dividing by root n. Okay, so I'm back on the book now, so I hope I've done that right and you can see it. Okay, so that's the central limit theorem, and that's why some of the questions, you'll see some of the answers are dividing by root n. Okay, yes. So then on the right hand side down here is where they go through doing your Z-score with your doing your hypothesis test with your Z-score, okay? So like I said, you're comparing it to 1.96 because 1.96 represents your plus or minus, your 95% basically that's in here in the middle. So again, if you're in there, if you're between 1% plus or minus 1.96, you fail to reject H0. If you're outside 1.96, either side, you reject H0. And again, be careful when you're looking at older questions because the wording also changed over the last few years. Failed to accept became the new wording, and the word reject was rejected, wasn't used anymore. So the wording changed. Okay, so use the wording that your teacher has told you to use for the current year. Okay, and it has changed a couple of times over the last 10 years. But out from that, the hypothesis test is the same, okay? So I'm just going to go through this example so that you can see the steps, okay? And then, of course, we'll practice through the exam questions. So a tire company claims that the mean life, put that word mean life of tires that it produces is 11,000 kilometers with a standard deviation of 240 km. An independent supplier of tires wants to investigate the company's claim. A test on a random sample of 144 tires from the company gave a mean life of 10,963. Okay, carry out a hypothesis test at the 5% level of significance to see if there is evidence to support the company's claim. Okay, so solution number 1. State the null and alternative hypotheses. So the null hypothesis, the company produces tires with a mean life of 11,000. Okay, that's what the company claimed. Who are we to argue with that company? We've no data to back it up. So therefore your H0 is that the mean life is 1,000 hours. Okay, the alternate then, you don't say it's less than 11,000 or greater. You say it's just simply not 11,000. So that's what I mean by you write it that all scenarios are covered. Because if you wrote that as in it's less than 11,000, then what would happen if you found a value that was greater than 11? You wouldn't be covered, okay? So basically it is 11, it is not 11. Okay, if you choose to do it the Z-score way, then you convert the given results into Z-scores. Okay, so you're using your standardizing formula. You're dividing by root n because it was mean lives. Okay, so it's the 10,000 minus 11, and you're getting minus 1.85. Okay, I recommend you draw a very simple bell curve. Mark in the plus or minus 1.96 and show that the minus 1.85 lies within. Okay, and that's it done. So you conclude then, okay? So I would say as my conclusion, minus 1.98 lies within plus or minus 1.96. Therefore, we fail to reject H0. Okay, and you go back to your words. The company produces tires with a mean life of 11,000 kilometers. Okay, and that's how you do a hypothesis test. You state the two, you conclude, you do your test in the middle. Could you have set up, instead of 2 and 3, could you have set up a confidence interval there? Yes. Okay, so your test data is still the same. So 10,963 is your p hat. Set up your, so just set up a confidence interval. And again, you're seeing, does it lie within it? Okay. And I'll do an example both ways in exam questions in the next couple of days. Okay. And then finally, I want to get on to p-values, okay, which is the final thing that can be asked typically towards the end of a question. You'd see a little p-value question. So a p-value, I'm just reading here, is used as an alternative method to make a decision on the null hypothesis. It's a probability value, okay? It's a measure of the strength of evidence to reject or fail to reject the null hypothesis. The smaller the p-value, the less likely the null hypothesis is true, and vice versa. Okay, the decision to reject or fail to reject H0 is based on the comparison of the p-value with the level of significance. Okay, so we always use the 5% level of significance. Okay, so therefore, the p-value, well, let me go back to the diagram. So we use the 5% level of significance is the exact same as the 95% level as well. So they're either talking about the 96 here in the middle, or they're talking about the 5% on the outside. Okay, so don't get confused with them. They're the exact same thing. Okay, and it depends again, the context of the question, whether 95 makes sense or 5 makes sense. Okay, so the 5% level of significance, 2.5% is here, 2.5% is here, or as a decimal, that's 0.025. Okay, so that's what I presume is here. You have 2.5% either way. Okay, so now let's try. I'm going to go to the example to show you how to do it with the test statistic. Okay, so a coal merchant, down here in the example, a coal merchant sells coal in bags marked 50 kg. The merchant claims that the bags have a mean weight of 50 kg with a standard deviation of 1.2 kg. To test this claim, a random selection of 72 bags were weighed and found to have a mean weight of 49.7. Sorry. Write down H0 and HA. Calculate the test statistic for the sample mean. So you can see we're on about means again. Calculate a p-value for this sample mean. And at the 5% level of significance, is there evidence to show that the mean weight of the bags of coal is not 50 kg? Justify your answer. Okay, now some books tend to write H0 and H1 in maths language as this. I prefer to also use English. I just think it makes for a better hypothesis test if you have the English to back it up. Okay, and you get all the wording from the question. It's not like you have to make it up. Okay, so my H0 would be the bags of coal have a mean weight of 50 kg. Okay, and the alternative hypothesis, coal bags or bags do not have a mean weight of 50 kg. Okay, so our test data is 49.7. Okay, so let's convert it to our score. So it's the same Z-score standardizing formula. So 49.7 minus 50 over, I presume 1.2 is sigma, wherever that is, yeah, standard deviation of 1.2 over the number of bags that you test. So we're getting minus 2.12. Okay, so how do we do it here? Okay, so I'll do it with Z-scores first, just to tie it into what we do. That sits outside 1.96. So you can see straight away there, you're not accepting H0, you're going to accept H1. Okay, so that's how you do it with Z-scores. Okay, but how do you do it with p-values? Well, you're basically looking at the area that's left over and you're comparing it to 5%. Okay, so let's look to see the probability that our test statistic T is less than minus 1.2. Sorry, our test statistic is less than minus 2.12. Okay, so we want to see, are you out in this area out here? Okay, now as you know, because of our tables that we use, we don't have negative standard deviations in them. Okay, so it's the same thing as twice the area up here. Okay, so that's 2.5%. So if I get the area up here, or the probability of being up here, and multiplying it by 2, I get the same thing as the total 5% that would be in the two ends of that normal distribution. Okay, so what you're doing there in this line here is basically you're just going 1 minus the probability of Z being less than 2.12. You would have done this with any Z scores. You're looking it up in the tables, 2.12. You're seeing that it's 0.9830, and you're subtracting it from 1 because it's the blue area up here in the right that you want to figure out. Okay, so you got 0.17. but that's only 2.5%, okay? And you're going to compare it to 5, okay? So that's why you multiply the p-value by 2 and you're getting 3.5% or 3.4%. You're saying 3.4% is less than 5%, so therefore you're going to reject H0. Okay, so that's the normal way that it's done in the Leaving Cert books. It's also perfectly acceptable. Do you see the 0.017? It's perfectly acceptable to say that's 1.7%, and that's less than 2.5%. Okay, if you just concentrate on the lower end, that's okay to say that too. Okay, it's the same thing. But the books tend to multiply the p-value by 2 and compare it to 5%. Okay, so I hope that makes sense. So that's what the p-value is. It's just you're working on the extremities out here, the 5% that's outside the 95% level or confidence level. You're working at the 5% level of significance, which means something has changed. And that's why it's called a level of significance, because if you're out here, the mean is no longer here in the center. It has shifted outside plus or minus 3 standard deviations away, and it's significant. Okay, so a good question on the 2019 paper on p-values. So I suggest you try that one. I'll do up a video for it, and we'll see, does the p-value make sense for you in that particular one? Okay, and that concludes our theory part of statistics. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.